All right, so this is for group homework. This is our second group homework that I have to do. And I was assigned to do and work on problem 5 here, or 4 here, I'm sorry. That says on a thin rod of length L lying along the x-axis with one end at x equals 0, and we have the picture there. There's a distributed charge per unit length given by lambda equals kx, where k is a constant with units of coulombs per meter squared, and x is the distance from the origin. Find the electric field at point P equals 0, y. So our electric field is going to be 1 over 4 pi epsilon naught, and then our integral from a to b of dq, our separation vector squared, and then our unit vector, which is our separation vector, in the same direction as our separation vector. So we're going to break this little segment here into a bunch of little charges and then add them all up. So I'm going to start by working with what we have and figuring out what we have. So dq is this small little bit of charge. And in the problem it tells us the charge distribution per unit length is lambda equals kx. So we'll do lambda times dx. That's our charge distribution. But we know what lambda is. Lambda is just kx. So dq is really kx dx. Okay? Vector r. Well, vector r is going to be from here to there. That's vector r, which is just pointing in the j direction. So we'll just say yj, because it's at the point right here, which is 0, y. We also need r prime. Now r prime is going to be, I'll do it in a different color, right here along our x-axis and along our charge distribution. So that's r prime. So r prime is just xi hat. It's a length x, and I hat because it's going in the I direction. Okay, so we have that, and now with these two, we can find our separation vector, because our separation vector is defined as r minus r prime, which r we know is y j hat minus x I hat. And then I'm just going to rewrite that so the I hat comes first. So that's going to be minus x I hat plus y j hat. And our separation vector, I'll do in red, is that guy. That's script r. Okay, so we have that. Now that we have script r, we can pretty easily find our magnitude of our separation vector, which is just going to be the square root of our components squared, right? So minus x I hat squared plus y j hat squared, which is just going to be x squared, the I squared, that's going to be just 1 because it's a unit vector, plus y squared. So that's the actual length of that separation vector. And then to find our unit vector, we can do this just how we would do any unit vector. We just take that, whatever that vector is, script r, and then we divide by the magnitude. And we have both of these. We defined them earlier. Here is r, so minus x I hat plus y j hat. divided by the magnitude, which we did here. So square root of x squared plus y squared. Okay, so we figured out what everything in this equation is. This equation we have for our E field. We found what dq is. We found what r is. If we need to square it, we can. And we found our unit vector script r. And everything else is just a constant. The only other thing we need to integrate with is length. So a to b. Well, we're going to integrate over our distribution, which is along the x-axis. So that'll go from 0 to L, from here to there. Okay, so now we know our bounds of integration, our limits of integration. So we can really substitute all this stuff in and start working through it. So then our E field is equal to 1 over 4 pi epsilon naught times the integral from 0 to L, now that we're substituting in our limits. dq we know is kx dx. Now we need script r squared, which we have, where is it? Oh, right here. So we square that, we get x squared plus y squared. And then that's going to be to the second power times minus I hat plus y j hat over the square root of x squared plus y squared. And I'm just going to move this dx over here because that's usually where we see it, right? Oh, did I forget a lambda? No, I have everything. So we have dq. This is dq along with this x. This is script r squared. And then this whole stuff here is our script r unit vector. Okay, so we have everything. All right. I'm going to factor out that k and just rewrite this a little bit. K is a constant. It's mentioned in the question that k is a constant, gives us the units as well. But the fact that it's a constant, then I can put that outside the integral. So this is just k over 4 pi epsilon naught, the integral from 0 to L. And then I have x divided by, so this term here, the x squared plus y squared squared, and this one, which I'm actually going to rewrite here as to the 1/2. We can just use our rules for exponents to put those together. So that's really just x squared plus y squared raised to the, and we need to add our exponents. So 2 plus 1/2 is 3/2. And then we still have times negative x I hat plus y j hat dx. Okay, so good start so far. We rewrote it. Now our E field is going to have x and y components, right? The I hat is telling us where our I component of the E field is. Our j hat is going to tell us where the y component of our E field is. So I'm going to break this up into basically two different integrals, and I'm going to start with doing the x component. So this is going to be the x I mean, if you wanted to, you could think of it as two additional integrals. I guess just to explicitly show it. We still have our E field is equal to k divided by 4 pi epsilon naught. The integral from 0 to L minus x squared over x squared plus y squared to the 3 halves I hat dx, and then plus another integral from 0 to L xy over x squared plus y squared to the 3 halves, and the j direction dx. And I should probably put brackets around these because this constant that I pulled out, if it'll let me, this constant, the k over 4 pi epsilon naught, that has to be distributed to both integrals. So that's a mistake that I could have made somewhere if I had a pitfall potentially in this question. I know that's something that my professor wants me to mention, possible pitfalls. Well, when you break this up into two separate integrals, make sure you carry this constant that you perhaps factored out like I did. Otherwise, you won't get the right answer. I don't think there are really any other pitfalls up until this point. It's been pretty straightforward, I think. It will get messy very, very soon. But okay, so we have this part is our I hat direction, so that's our x component. And this is our j hat, so this is our x component. And this is our y component of our E field of E. And of course we have our constant that both are going to be affected by and scaled by. But just to make things a little easier, I'm going to solve the I component first, then I'm going to solve the y component, the j component, second. I'm going to add them together, and then I'm going to multiply by our constant. So that's kind of the game plan, that's kind of the strategy here. So I'm going to start with the x component. Okay, so our E field in the x direction is going to be, well, I'll just write it out explicitly first. K over 4 pi epsilon naught K over 4 pi epsilon naught, the integral from 0 to L, and then everything that's on the inside here. So minus x squared over x squared plus y squared to the 3 halves dx. And I'm just going to pull this negative out. It's a constant, so nothing wrong with that. And now we're going to have to integrate this guy. And you see we have a term squared in the numerator. And more important than that, we have something in the denominator that's being raised to a fractional power. And really the only way we can solve this is with trig substitution. If you didn't know to do that when you got to this point, you could try other methods, but they're all going to fail. So if that's something that was like a pitfall for you, you don't know how to approach this, I would try U sub first. Obviously we can't just do this like a power rule, so that's off the table. A U sub, well, I could let U be x squared plus y squared, but then du is just 2x, and I have a factor of x squared, so the U sub's not going to work. We're not multiplying two functions, so integration by parts, even if we weren't doing that, there's what do you let U, what do you let be dv? Integration by parts isn't going to work. Really, all else fails, we're going to have to use a trig sub here. There's no other way to go about it. So the way that we do this is I see we have an x squared in the numerator. So I'm going to let x, I'll do it here. I'm going to let x be equal to y, that's our number here, times tangent of theta. Okay? And if you do that, we can see that theta is going to be equal to tan inverse of x over y. Or you could also just say x over y is equal to tangent theta. They're all equivalent statements. But this will help us get our orientation understood later, because that's another possible pitfall, but we'll come to that in a little bit. Dealing with just this equation here, I could differentiate both sides with respect to theta, and I'll get dx d theta is equal to, well, y is just a constant with respect to theta, and the derivative of tangent of theta with respect to theta is just secant squared of theta, so know our trig derivatives, that's important. And then I'm going to solve for dx, so I find dx is y secant squared of theta d theta. And I'm doing that so I can, let me unhighlight this. I'm doing that so I can replace this dx. I know what this dx is, so I can replace that in terms of theta. X I know, so I can find x squared if I just square. I know what x is, right? So if I just square both sides, I can say x squared is equal to y squared tangent squared of theta. So now I know what x squared is, and that also works for this term in here as well. Okay, so now we can substitute everything in our E field, and the x direction is, we have our constants out front. We're integrating, so we kind of have two options here. I'm going to just back substitute. So I'm going to do a to b. And the reason I'm not doing 0 to L is because our integral is going to be, it's going to have all thetas in it, where 0 to L only works for x. So 0 to L only works for x. So I'm going to call it just a and b, and then when I back substitute everything in terms of like x, I'll use the terms 0 to L. So okay, let's just plug everything in. We have x squared, but we know what x squared is. That's just y squared tangent squared times dx, which is just y secant squared of theta d theta. And we're going to divide that by x squared plus y squared. So y squared tangent squared of theta plus y squared. And that's all to the 3/2 power. Okay. So I'm going to do a couple steps here. So far I'm just rewriting it out. I can combine obviously this and this, and I get y cubed. So y cubed, and then we have tangent squared secant squared of theta d theta. And then I'm going to factor out a y squared out of the denominator, and I get tangent squared of theta plus 1. That's all to the 3/2 power. And so I just rewrote it. I factored out that y squared. Nothing here to say about the numerator, so I'm just going to rewrite the numerator. Oh, there's one more thing I want to say up here. If you get confused on what to do here, like what to let what be, just think about what you need to actually substitute in, because essentially what we're doing is we're substituting anything that has to do with x, like x or dx, with things that have to do with theta. So if you forget that, you can kind of think of like, oh, what do I do? Well, I need to know what dx is. Let me take the derivative with respect to theta of both sides and solve for dx. So just something that might help you out if you forget, because it's been a while for me since I've taken Calc 2. Okay, so y squared to the 3/2. Well, we can just do our rules of exponents. So a power to a power, we multiply. So y squared to the 3/2 is y to the second times 3/2. So that's just y cubed. And then tangent squared of theta plus 1, well, that's really secant squared. And we get that from our Pythagorean identity. To the 3/2, I'm sorry. So if you forget that, I'll make a note over here. You can do sine of theta. This is Pythagorean's identity. Plus cosine theta equals 1. Now, if I divide both sides by cosine squared, I'm sorry, these should be squared. If I divide both sides by cosine squared of theta, well, sine squared over cosine squared is tangent squared. Plus cosine squared divided by cosine squared is 1. And 1 over cosine squared is secant squared. Right? So we found this is right here, and we just substituted this guy in. So that's where that's coming from. And again, you don't have to memorize all that. As long as you know just the first Pythagorean identity, sine squared plus cosine squared is 1, you can derive any one of these that will come up here. So obviously we can see here the y cubes drop, and we get tangent squared theta times secant squared theta d theta. Secant squared, so we can do the same exact exponential rule we did with y cubed, right? With secant squared. And you'll just get secant cubed of theta. Which I think we can see that this secant squared will drop with all but one secant there. And we just have tangent squared theta over secant theta d theta. Okay, so I'm going to start by, well, I guess start by rewriting this out. Okay. Secant of theta, just using our reciprocal identity, this is just cosine theta. So I'm going to just move that up, call that cosine theta. And then tangent squared, well, I could do the same over here, and I can see that tangent squared of theta is equal to secant squared theta minus 1, if I just subtract 1 from both sides. So I can do that. Just say that this is secant squared theta minus 1 d theta. And then I'm going to rewrite it in terms of cosine here. So really my goal is I'm trying to write everything in terms of cosine using trig identities that we have. So we have cosine theta. And now secant squared we can pretty easily write as just 1 over cosine squared theta minus 1 d theta. And then we can multiply, we can distribute this cosine theta into each term. And if we do that, we're going to be left with just cosine in the first term. So just, we have 1 over cosine, that's just the same as secant of theta. And then just multiplying by -1, we get negative cosine theta d theta. Okay? Well, now we can break this up into, I know I've already broken this integral up into x and y components, but we can do it again by using the property of linearity. And we can just say that this is the integral from a to b of secant theta d theta minus the integral from a to b cosine theta d theta. Okay. And these are either integrals that are standard integrals that you can find on an integral table, or you could just solve remembering your trig functions. So secant, the integral of secant of theta is the natural log of tangent theta plus secant theta. So that's this first integral minus the integral of cosine. Well, let's see. The integral of cosine is just going to be sine, so that's going to be negative sine theta. Evaluated from a to b. Okay, so now we need to back substitute everything. And the way that we're going to do this is recall that tangent theta. So this I did at the very beginning before I substituted everything in. Is equal to x over y. But we know that tangent of theta is just your opposite over adjacent. So if I were to draw a triangle here, to the best of my ability, okay, a right triangle with some angle theta that we've been using, well, the opposite angle should be x, and the adjacent angle should be, or I'm sorry, the opposite side should be x, and the adjacent side should be y. And this was a pitfall for me. I want to make note of this. Is I'm so used to just kind of blindly saying that, oh, up and down, that's y, and left to right is x. And okay, it is when I do my coordinate axes, but the side of this triangle is going to be dependent on this. And then just use what you know about right triangles to find it. And obviously, the hypotenuse is just going to be the square root of our two sides squared. So the square root of x squared plus y squared. And that is the hypotenuse there. And we need to know that because we need to know all of these, we need a back substitute here. So let's just start with sine theta. We need to know what sine theta is because it's here. Sine theta is opposite over hypotenuse, and the opposite is just x. And we know the hypotenuse is the square root of x squared plus y squared. And you can factor out an x squared from the denominator and inside the square root. You'd get x squared over y squared plus 1, all square root. And then obviously the square root of y squared is just y. Square root of x squared over y squared plus 1. And that's sine theta. There's a tangent theta in there, but that's the easiest one. We already said that's x over y. So we have sine theta, we have tangent theta. We need to know what secant theta is. And then once we have secant theta, we can plug all this stuff in and we're good. Okay, so secant theta is equal to 1 over cosine theta. That's our reciprocal identity. So it's just cosine flipped. Cosine is our adjacent over our hypotenuse, but because it's secant and we have to flip it, it's going to be basically our hypotenuse over our adjacent. So x squared plus y squared, square root over y. Again, we can do the same trick by factoring out a y squared, and you get x squared over y squared plus 1. Divided by just y. And again, we know that y squared, that factors out. You get y square root x squared over y squared plus 1 divided by y. And we can see that the y's cancel. So finally, we can say that our secant of theta is equal to just x squared over y squared plus 1 square root. And we can substitute that in for secant theta. Okay. All right, so it's a bit of a process here. We have to plug it all in. We're going to get minus k over 4 pi epsilon naught, the natural log. This is going to be big. So we have tangent of theta, which is x over y, plus our secant of theta. So let's plug that in. Secant theta is going to be just where are we? Okay. Yeah, this is all in the tangent or in the natural log there. So those are two kind of separate things. That's where I was getting confused. So another pitfall. X squared over y squared plus 1. Make sure you draw these parentheses. I like to draw parentheses like around my thetas here. So it can be a little confusing sometimes for me. So let's just make sure we know the natural log, because that's only coming from secant. And then minus sine. And now that we've back substituted, I don't have to write from A to B. I can go from 0 to L like we originally were going to. Didn't I factor out here? I think I did. Yeah, this is, I factored out a sine. Yeah. So this should actually be x over, it's the same thing, but I just factored it out. I want to write it how I had it. Okay, so now that we have that, and this is all our E field and the X. We still have the Y direction to do, but that one's a lot easier. Draw that a little nicer. So we have our constant out front. And let's see, let's start subbing in here. So we have the natural log of L over Y plus L squared over Y squared plus 1 square root minus L over y, the square root of L squared over y squared plus 1. And then we have to do minus all that other stuff. So just looking at it real quick, what do we get? If I plug a 0, that's going to be 0. That's going to be 0. So I'm going to be left with just, yeah, so let's see. We plug that in. You're going to get the natural log of 1 because you just have the square root of 1. And the square root of 1 is just 0, so minus natural log of 1. And then obviously if I plug a 0 into there, it would be plus 0. And the natural log of 1 is 0. So that whole, the 0 gets rid of everything. Okay, so just to write it out real quick, our E field in the x direction is minus k over 4 pi epsilon naught. The natural log of L over y plus L squared over y squared plus 1 minus L over y square root of L squared plus y squared over 1. And this is in the I direction. So very messy, but okay, we have it. And now we can move on to the y part. Now it's going to be, essentially, we're still going to have our k, so we still have our k over 4 pi epsilon naught, the integral from 0 to L. And if we go up here, we have xy, x squared plus y squared to the 3 halves j hat. So we can go ahead and put those guys in. So let's see, we get xy over x squared plus y squared to the 3 halves dx. And let's see, y is a constant, so I can pull that out. And integral from 0 to L. I don't have to change these limits because it's still in terms of x. If I do a substitution, which I will be, then I'll have to not do that, but we'll get there when we get there. And in fact, I see I made a mistake when I was doing this homework problem on my own because I wrote this as the square root of x squared plus y squared, when it should have been x squared plus y squared to the 3 halves. So I'm kind of going blind here, but that's okay. That's a pitfall that I should mention. This should be to the 3 halves, not to the 1 half. So just be careful with all of that stuff. But I don't think that really changes anything too much. We can still solve this using a u substitution. We don't have to do any trig sub, as long as we let u equal x squared plus y squared. So my function in here. Then if I take a derivative with respect to x on both sides, I get just 2x, y is a constant. Or du equals 2x dx. I want to substitute in, so I already have a substitution here. That's just u. I want to know what x dx is, and then I have everything. So 1/2 u du equals x dx. Okay. So let's see. Let me move this down just a little bit here. I can just erase it. Our E field in the y direction, we have our k, our y, our 4 pi epsilon naught. Okay. I'm going to keep the integral limits off again and just say from a to b. And what do we have? Well, x dx is just 1/2 du, which I'll put at the end. And this is u to the 3/2 du. So now it's just a pretty simple integral. So I can factor out the 1/2. That's obviously just a constant. I'm going to write it like this, though. In fact, here's what I'll do. Why am I doing this? Well, the 1/4 pi epsilon naught, it's just a very popular constant that comes out a lot. So I just want to, I guess, separate that, I suppose. And then this is the integral from a to b. I'm going to move the u up to the numerator using our rules of exponents, right? And now this is an integral we can do without too much problem. So this is just a power rule. So I'm just going to write it out. So if we add 1 to this, this is going to be -1/2. So we're multiplying by a -2. So let's do this. -2 over the square root of u, evaluated from a to b. Well, now that 2 actually cancels if we pull out the 2, which we can because it's a constant. And you're going to get -1/4 pi epsilon naught times y, ky. And now I'm going to just back substitute, so that's going to be 1 over the square root of x squared plus y squared. And now we're evaluating it from 0 to L. So your E field, if we plug that in, -1/4 pi epsilon naught times k times y is 1 over the square root of L squared plus y squared minus 1 over the square root of y. If we back substitute, or not if we back substitute, if we plug in our 0. And that's basically all of it. I'll write it out like this. I'll do one more last write out. 1/4 pi epsilon naught times ky over the square root of y, which I don't need to rewrite that, I don't think. I think it's fine the way it is, minus ky over the square root of L squared plus y squared. And if you wanted to, you could do some simplification. Like, for example, you could factor out a y squared. This is in the j direction. I mean, you could. I don't know if it's really helpful. 1/4 pi epsilon naught. Let's see, that's just k times the square root of y minus, if I factor that out, that'll be L squared over y squared plus 1. And obviously the y's drop. Not sure if that's helpful or not, but it's there. And yeah, that's basically everything. This is in the j direction. It's a long problem, a lot of trig subs. Hopefully I explained how to do it correctly in enough detail and gave some tips on how to solve it, as well as showed you possible pitfalls. So hopefully that explains everything clearly.